Alright, so now that you've collected the data, let's take a look at it in Excel and start preparing it for your lab report. So as you can see in this setup, I've got the data just kind of in here as a simple data set. We have our raw data. We don't want to do anything with that data, but I'm going to go ahead and create the second page, go back, and I'm going to capture all the data at one time and pop back into the screen, paste it in, and it's oftentimes a good idea to get a quick glance at your data before you begin manipulating. You did this already when you did your previous lab activity with falling data, and now we're going to do that again and get a good look at it. But I want to kind of give you a bit of a shortcut here. So what we'll do is I'm going to highlight the first two items, first two columns, go to the insert. Most of the stuff at this point I'm going to assume that you've done at least enough times that you have a reasonable familiarity, so I'm going to just kind of bop, hit the stuff and move on. So as we did previously, I just am going to create a graph that is position versus time. I'm going to manipulate it a little bit so that I can fill up the space here. You'll notice that it doesn't fill up the entire space. I'm not really sure why this presets are that way, but it is what it is. So first thing that we'll do is, you see how I stretch it out because I won't be able to see all three graphs, just like you saw in your pre-lab activity and in the capstone setup. So I'm going to zoom in like so. I'm going to go over here to quick layout. Let's go ahead and throw just all the basics in here. We need the axis title. This one's going to be position in meters. Pop over here and we'll do time as usual. Most of your horizontal axes are going to be time, and if you tap on the horizontal axis you can right click to format axis, unless you, as you can see, already have the format panel open. So I'm a format axis. In this case I'll just tap it for you to see. Well, you can't see the pop-up menu on this screen recorder, which is another obstacle. But so we come over here and you see it goes all the way 8 seconds. Let's change that 8.0 to 7.0 tab, and now that fills up the space better. You might get rid of these major grid lines. I like to go in there and put a solid, a solid border around. Make sure that's a solid black. And one other thing that I'm going to do is I'm going to take these data points that are blue, I'm going to go ahead and just make them, go over to marker, we're going to change those and make the fill solid black and no border. We're going to shrink them down a little bit too, because these are the guidelines for the eye. This is just the data. So we click here, stretch this out. I'm just playing with the formatting right now, and we'll leave this here. Oops. We'll leave this here for now, but a legend in this one is probably going to be a little bit less informative than anything else. Okay, so this is the rough draft of the data, and what I meant by a quick version of this is you can go ahead and highlight your column A and C, column A and D, and it gets a little bit time consuming on that, a little time consuming. So one thing that you can do, you've already got this format, it's already ready to go, so let's copy and we're going to go right below it and we're going to paste, and we're going to paste a third time because we want a velocity versus time and acceleration versus time. So squeezing these all into the view panel here, and I'm going to leave this format panel open because it might come into use. But now this is going to be velocity versus time, so let's change it to velocity in meters per second, and then when you go back into once you get out of the axis title, you can right click or go select data, and instead of this is not position data, so we're going to edit this position data. We're not no other tricks. We're just going to change that name, point it to velocity versus time, and then instead of column A, I'm just going to type right here, and you can't see it, but you should be familiar enough with how to do it by now. Be careful not to use errors, but change your B's with C's. And if you do that and then just click OK, you don't even have to go and scroll or anything like that. You saw it change, and now this is your velocity versus time data that you saw in Capstone. And there's some stuff that's going on there, and we'll discuss what that is. I think you probably would have guessed by now what that might be. And then we'll just do the same thing for the acceleration versus time. Let's change that title, acceleration versus time, and that's in meters per second squared. Can we do that if we go up to home and we launch the font window? Yes, and we go to superscript, and then there it is, meter second squared, formatted nicely. Right click on your data or the chart space, edit again. We're going to point the first one to acceleration versus time, D1, and then this is going to be column D instead of B. So, and it doesn't even have to be capital, just use lowercase, it'll automatically fix. And you change it to D, boom, and now you have your 3 graphs. That was pretty quick. Hopefully it'll feel as quick for you. What's really going to slow us down on this is, let's see if we can really pin down the best information to get from that. Now, you look at the first graph. Now you see the curve area here, the curve area in the middle of the movement, and the curved area at the end. Those are going to be your most likely constant acceleration spaces. And you notice that there's a straight line here and a straight line here, and those are constant velocity spaces. So we've got to sort those two out. And what's really nice about this analysis is that we can borrow data, so little bits of data that will apply to different spots. In the velocity space, you have a wobble here, but for all intents and purposes, it looks like the average in that range is probably pretty constant. And when you look at the acceleration versus time in that same basic period of time, you see that it wobbles more, it's more pronounced, but it's averaging around 0. So we're going to use that range to select what we want. In this range, if you notice, and it doesn't have to be exactly right, but you see that you've got a straight line going here. That's constant change in velocity. You have a constant change of velocity here in this mid-range, and the constant change of velocity in this third range. These three, if you'll notice, correspond to the curved areas above. And our question now is, well, are those constant acceleration? Let's take a look at that. And here in the acceleration space, the acceleration is fairly constant, non-zero in this range, corresponding to that first bit, you speeding up to walk backwards. And then in the mid-range where it is constant change for velocity, you see that it bumps up, and it's not beautiful, but it's non-zero, and it's a negative value, so it's a different acceleration because your acceleration is changing from you moving this way to go this way, so the acceleration is coming back towards the sensor. So that's consistent. And then again over here at the far right, you've got some reasonably constant acceleration that corresponds to the change in velocity here and so forth. We don't need to capture all that information. We just need to find one region of constant velocity for the 3 data sets that's shared, and then one region of constant acceleration for the data sets that are shared. Let's deal with constant velocity first. Constant velocity, we expect that the position is going to be a straight line area, so that's over here and over here, these two areas. So I'm going to look at this and come over here and I'll say, well, the average is kind of all somewhere between, let's say, about 0.6 or 0.7 seconds all the way out to about 3.2, 3.1. So I'm going to use the range just to kind of be a little bit conservative here. You can go a shorter range in here and just use intermediate spaces in there, but I'm going to go ahead and just kind of do the full range to demonstrate that the overlap of the data points can be instructive as well. So for the position versus time, so that's it was 0.7 seconds all the way to 3.1 seconds. So I'm going to highlight that on all 3 graphs. So if I right click on the position versus time, I'm going to select data. We've got the position versus time. Let's change that name. We're going to call that raw. I know that we called it something a few minutes ago, just use the pointers, but that was a quick thing. So I'm going to call this raw position. Well, I'm just going to call it raw data. Then we're going to add constant velocity. Nope. Yes, constant velocity. We want constant velocity as the label because that's the condition of motion that's happening here. And then we're going to just simply go and capture that data. In the X value, we say we're going to go from 0.7 to 3.1. Remember, in your data, it'll probably be different data points, so make sure that you don't just arbitrarily capture this. You want to capture what works based off of the data that you're looking at that you collected. Click on this, come down, capture the position versus time for the condition of constant velocities. We've got some velocities and positions and everything that's kind of flying about, so let's make sure that we're clear on that. And you see the dots are populated in place. I'm going to go ahead and click OK. Click OK. You will want to change this, and I'll change it for this one, but I won't spend the time on the other ones just for time purposes here. But you'll want to change the marker to a different shape or make it larger. In this case, I'm just going to make them larger. Boop, 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 boop. And now it stands out a little bit more. Probably we'll also go with a different shape for the acceleration, but or you can make them open. So in this case, we'll leave that as is. Now I'm going to go to the other two graphs and reproduce this also for the same range. We're going to edit this. Data is no longer, this is raw. And we're going to add constant velocity. And if it's consistent, it should look like a constant velocity range. All we're doing is highlighting them so that we can see where those ranges correspond to each other. So that's the X's. And that's the Y. Also 0.7 to 3.1. We're using the same data range in both. And click OK, and then we'll come down to acceleration and repeat the process. Raw, click OK, add, constant, and you might even try to just kind of copy and paste. Be careful not to use arrows. 0.7 to 3.1, and this is going to go from the time 0.7 to the time 3.1 seconds. Click OK. Uh-oh. I used the velocity instead of acceleration. Let's fix that. So now you see what it's done. And you might think, okay, well, there's a little bit of a tilt here, but remember that these outliers here will cancel out these outliers here, and they overall will expect, we're going to do a calculation to confirm that the acceleration is either 0 or very close to 0. But now you can see the data points illustrated here for constant velocity. Now we want to identify constant acceleration, and the trick here is that your acceleration ranges are largely very narrow compared to the constant velocity. So which one is going to give us the best information? I think that the best information is probably the middle one, but you can consider doing the start or the finishing accelerations. Use the best data that you have to get the best judgment and make your best judgment from there. So in this range, I see that this data point 3.1 seconds can be maybe a little bit in line with the data. Maybe it's it's more clearly going out. I'm going to include it here. I want you to use your best judgment. That's what science is making your best judgment and doing the best you can. This comes all the way out here to about 4.0 seconds. So we're going to do from 3.1 to 4.0 seconds for constant velocity, constant acceleration, because it's really hard to nail it down with the acceleration information. The velocity information really is kind of the best graph to use for really selecting your data ranges. So let's go back up here. What we say, 3.1 to 4. So I'm going to right click up here, select data. We've already done that. Let's add constant acceleration. And for the time, we're going to go from 3.1 to 4.0. And then same thing for the position, 3.1 to 4.0. Enter. Enter again. And in this case, like I said, I'm just going to do the marker right here, but I recommend that you do that separately. So I'm going to make this one solid. And you always just kind of want to think about what does this look like when it's printed in black and white. In this case, I'm going to put no fill, and I'm just going to make it really large. And now you can distinguish the solid dots, the solid large dots, the open large circles. Those are both data that you are selecting to do analysis with, and the small dots just represent the raw data. And there you go. You've described it in your notes or in your lab report. So we'll go ahead and go to the other two and add it as such. And I'm going to skip this part for you guys. Constant. And voila, there we go. All three of the data that you are identifying as condition of constant velocity and condition of constant acceleration. You can use your own shapes choices. I just want to give you the sense of where to go with this. These three graphs are ready, almost ready for just pasting into your lab report. And 3, 2, 1, there you go. Now it has also trend lines in particular places. In this particular lab, you can do trend lines for all these and still kind of get where you're going, but it's a little bit more direct if you or a little bit less steps if you just get the trend lines for your position versus time. You have a linear trend line for the constant velocity and a parabolic or a quadratic order 2 lab. And let me just kind of click on that so you can see that here, that's polynomial order 2. I said quadratic, but it's the same thing. Polynomial order 2 for the position versus time only. And remember, it's because it looks like it's a graph, and when we change it from linear to polynomial, the r squared value increases significantly from 0.68 or something to a really good fit. So there you have it. And you'll notice that the one shared data point has both data points illustrated the way that I've done it. And now the next step is to extract the data as seen in your lab manual and compare that to the average of the values. And the way you type the average of those values, you just simply highlight the values you were interested in. Well, you type equals average, open parentheses, highlight the data set that you want, close the parentheses, hit enter, and there's your number. Then you can calculate your percent differences between the average and the slope from the preceding graph, if you will, and put that into a table and put that into your lab.